All right, let's talk first about one like 3, 4, 5, and 6. Maybe we can take number 5 possibly. It says that you're supposed to, well, remember 3, 4, 5, and 6 yesterday I said that some of those would be, they were worded weird. One says, is this the equation of the tangent line? Show that this is the equation of the tangent line. Find the equation of the tangent line. To me, they're all the same question, really. You do your work. I mean, if you're supposed to show that something's the equation of the tangent line, just do your work to find the equation of the tangent line, and you'll have it. So on number 5, they had told you that the point was -2, 1. I don't remember. I don't have my book open. I don't remember how they gave it to you. Did they give it to you as y of -2 is 1? Or did they give it to you as a point like that? Oh, okay, whatever. So in other words, they're saying at this point on this y graph, we want to have the equation of the tangent line. And they tell you that the differential equation is y prime. What is the differential equation on 5? T squared y. That's it. Okay. And so actually, I guess technically I should make this instead of x. I guess I should make this t. If the input variable is t, then we really ought to have our tangent line have x and t. Because think about what you'd be talking about here. You'd be looking at a y graph where t is the input variable. So therefore, any line that is drawn on that grid would have t as its input variable. So we really probably ought to have t in there instead of x. So the idea is that we use our differential equation to get our derivative. So we've done derivative multiple ways, right, on the equation of tangent line problems. Back in chapter 1, gave you a y graph, and you would maybe sketch the tangent line and estimate what the slope was. Or then when we learned our formula rules, we would actually, we could do the derivative and plug in our value and find the slope that way. And here now we've got differential equations, but differential equations also have a derivative in them, so you can get the slope that way. So we take our -2 and we put it in, and we put the 1 in for the y, and we get 4, right? So we'll have 4 for our slope, we'll have -2 in here, we'll have a 1 in here, and now since you were supposed to show, or whatever on that one, you go ahead and do that, and so that would be y equals 4t plus 9, right? And so I think on that one you were just supposed to find it? You're supposed to find it? Okay. So you could have stopped here with this first one, right? Now, those other ones, they would have said something like, show that y equals 4t plus 9 is the equation of the tangent line. So in that case, you'd probably have to simplify it down. And your work would be your show. Okay? All right. Then the next segment, 7 through 14, let's go through those. And just kind of write down what we had here for those answers. So number 7 we did in class. Which one did that match up with? Roman numeral 7. Okay, I believe that's right. Number 8 is 1. Number 9. What was 9? 9 was Roman numeral 3. Yeah. Number 10 was Roman numeral 4. Okay, and we can go back and talk about some of these. Number 11 was which one? Number 11 was 8. Okay. Number 12 was 9. Number 13 was 10. Number 14 was 6. Okay, that's what my answer book shows anyway. Okay, so we didn't use all of them there, but anyone you want to look at there? Yeah. Okay, the blue dots were just like some initial conditions. Okay. Now, I think in the directions it said something about sketch the solution curve through those dots, but I had said yesterday, otherwise you'd have to lay your paper on top of it, you know, to kind of, and so I wasn't worried about doing that, although we're going to do a worksheet, one of the worksheets we have today, you will do that. So what it would look like is if you had let's just do a couple of them. So if you had this differential equation here, and then I gave you this initial condition, which would be like giving you y of -2 equals 2, right? That'd be this point right here. So if I gave you that initial condition, because this slope field represents all the possible solution curves, right? All the possible, remember the solution is the y function, the original equation. So that's what this is y and this would be t. And so this slope field is a kind of a picture of all those solutions. Well, if I give you an initial condition, that narrows it down, and the term is general solution. The slope field shows the general solution, which means like with the plus c in it. So there'd be multiple possible solutions. And then the initial condition gives you a specific solution. And that's where we would sketch in. So what we would do is just go through this point, kind of follow the lines, maybe something like this, you know, something like so. That would be your solution for that initial condition. Now, if I gave you this initial condition, which would be like y of 1 equals -1, so with that initial condition, our solution would be, you know, more like maybe that, right? So that's what the blue dots were for, was to then draw the solution given that initial condition. Now these are two different solutions. Here's one with that initial condition, here's one with that. So on the quiz, what I might do is, you know, give you a matching situation like this, and then say, you know, on this, you know, put a dot there like this and say, draw the solution curve through the given initial condition, or I might just give you an initial condition for all of them or whatever, and say, draw the solution curve in the slope field for them. Okay? But it's important to understand what the slope field represents. The slope field represents the shape, the slopes of the y graph, so it kind of gives you a picture of what the y graphs would look like in there. But what you would need is some initial condition to know where to put it exactly. And then you just kind of go with the flow of the slope. So let's see if there's another one. Sometimes it get a little tricky, quite honestly, with when you get some asymptotes and stuff like that. Some of these are pretty simple, but one like this, for example. All right? If I give you this initial condition up here, then you look at this solution and it kind of comes down, you see these, and they seem to be kind of leveling, and so you probably have a horizontal asymptote there. But now what's happening up here? It seems to be kind of leveling again, more like this, and then it's got to come back down, and if I'm following those lines, they're kind of coming down, you know, so I think that one would be something like that. All right, and then you probably have the same thing on this side, okay? Kind of a bell-shaped kind of effect. Let's do another one. I think there's another one in here that might be. But you didn't have to use those blue dots. So when you were checking, right, we talked about narrowing it down and then checking, plugging in numbers to get the slope. You didn't have to use these blue dots. You could have used anything you want. And we certainly could do one of those checking ones if you want to. I mean, because that's how you have to do that matching, is by plugging in some numbers and checking. Now, this would be a pretty easy one to draw, I would think. This one's not, this one's pretty easy. You know, to me, this one's just going to come down and then level off right in here, right? Kind of a horizontal asymptote situation. This one's going to come up and level off, you know, there. Yeah, let's look at this one. Okay, so 14, if you were going to actually draw this is more of a hyperbola or branches of a hyperbola kind of thing. I think this one looks like it'd be coming in like so and leveling off. It would be kind of a vertical asymptote there, so I guess this one isn't all that interesting. But you know, and it'd be the same thing in this side or the same thing here, right? Now you notice what does get interesting about this is right in here. What was this one, number 14? Which one? What was the differential equation for 14? Negative y over t, right? So what happens if you put in the point 0, 0? It's undefined, right? The slope's undefined, but it's undefined in kind of a strange sort of way. A lot of times we think of undefined as a vertical slope, right? When we talk about the slope is undefined, we talk about vertical. Well, that happens whenever t is 0 and y is something else. So this is actually something we're going to talk about on Monday. Well, we have talked about it a little bit already. Remember when we were doing limits and we said if you get 7 over 0, that's undefined, but 0 over 0 is a different kind of undefined. Remember that? If on a limit problem you get 0 over 0, you got to keep going. There might be a limit. But if you get 7 over 0, that does not exist. And what it means is an asymptote. It means it's 7 divided by a really little number, which is a really big number. But if you take 0 divided by 0, that's like a little number divided by another little number. What does that mean? It's something special. So a non-zero number divided by 0 means infinity, vertical asymptote. So if y is anything but 0, right? So if your y values are anything here, here, and here, and you're on the y-axis, so t is 0, you would have 1 over 0, 2 over 0, 3 over 0, negative 1 over 0, negative 2 over 0. Those all mean infinity, so those are all going to be going up. But if you get y is 0 and t is 0, right at the origin, you have a whole special kind of undefined. And in this case, it's just kind of this whole, because what you would have is you'd have branches here, you'd have branches here, you'd have branches here, and you have branches here, and it would never go through 0, 0. Okay? It's just kind of this weird spot in that particular graph. Okay? So it does get into some kind of interesting things on some of these slope fields. All right. Anything else on the matching? As far as plotting the points or looking at that, right? Because when you plot the points in a differential equation, you're getting out the slope, right? The slope of these little segments. All right, well, let's go ahead and talk about number 23 then. Matter of fact, before we do that, let's talk about the quiz real quick then. Maybe you want to jot this down in your notes. The quiz is going to be on sections 4.1 and 4.2. Okay? So, out of 4.1, we're not going to start new today. So, we've pretty much done what it is you need to know for 4.1. So, we're going to practice that some more today. Now, the Newton's Law of Cooling, we're going to go through that pretty detailed because I'm not assigning another one of those today. Now, when we review next week, we'll probably practice that again. So we'll talk about that. But so we're definitely going to have to do some matching on slope fields, right? Matching slope fields with their differential equations. Okay, so we're going to have to do that. So today's homework is going to have some of that. You're definitely going to have to draw slope fields. So we're going to work on that today. And you're going to have to solve a cooling problem or problems, right, using Newton's Law of Cooling, which for the most part we would be using this, right, the solution to Newton's Law of Cooling is what you really want to make sure you know, right? The solution to Newton's Law of Cooling is the equation you do your work with, right? I mean, you need to recognize the differential equation also. Okay, so those are the three things we have to be able to do coming out of this section. All right, so let's talk about number 23 and Boris and Natasha. Right? Did anybody recognize those names? It's an animated thing. It's Rocky and Bullwinkle is what it's from. Rocky and Bullwinkle. Boris and Natasha were like Russian agents. Yeah, yeah. Natasha was a tall, skinny, dark hair, evil. Yeah. Anyway, and Rocky and Bullwinkle, one was a moose. I think Bullwinkle was a moose, and Rocky was a squirrel. Squirrel and a moose, yeah. Anyway, it goes back a long time. So that's what this is from. Okay? But beside the point, but that little bit of the supposed humor of the authors, they throw some of those things in once in a while. Now, well, and I didn't even mention this earlier. We saw Newton's law of cooling in chapter 2 when we were doing differential equations, and there was a problem about it was a problem about a fund drive where they wanted to raise $65,000. I don't know if you guys remember this, but they wanted to raise $65,000, and they were talking about your book author said, according to Alfred E. Newman's law of cooling of enthusiasm. Now, anybody heard of Alfred E. Newman? Yeah, it was a play on Newton's law of cooling. Alfred, you ever heard of Mad Magazine? Yeah. Mad Magazine. Alfred E. Newman's the character with a big gap between his teeth. Okay. So anyway, but according to what they were talking about was Alfred E. Newman's law of cooling of enthusiasm was the rate that people give. Y is the amount that's donated. And what they said is the rate that people give is proportional to the difference between how much has been given and the target amount. So what they're saying is when there's a larger gap, remember what we talked about? I mean, this is what Newton's law of cooling says. The bigger this difference, right? The bigger the difference between the temperature of the coffee and the room temperature, this number would be bigger in the beginning when the coffee's really hot. And so therefore this would be bigger, right? The rate that it's cooling. And that makes sense, right? That makes sense. The bigger this difference, the faster it's cooling. All right? And what they were saying is that's true in a donate like Goodwill. You're raising money for Goodwill. And I think the problem said you were trying to raise $65,000. Here's the amount already raised. Here's the amount that they want to raise. So when this is a bigger amount, I think they have these two switched, so it would be positive. But the bigger this difference, they're saying the faster people donate. Like in the beginning, you get a lot of donations in. Then towards the end, why would it slow down? Right, that could be part of it. Now, some people might argue as it gets close, people get excited about, hey, putting it over the top maybe or something. But, I mean, what would be the biggest reason why as you get closer that there's less donations coming in? People have already donated, right? A lot of people have already donated. And the big donors a lot of times come in right in the beginning, right? I mean, they okay, here's this thing, and they go out and find people, and the big donations come in. And so a lot of times it's much slower as it goes up. So again, it'd be the same thing as these two numbers get closer together. So this just points out why we have differential equations. Because whenever we're interested in the rate that something's changing, differential equations are a really good way to describe what is happening. This is a really nice little, easy-looking formula to describe this situation. The bigger the difference between the coffee's temperature and the room temperature, the greater rate it's going to cool. Now the problem is finding that rate and then finding what the temperature is at all these different times. Well, that's why we have this solution to the differential equation. So differential equations are great for describing real-life situations. That's why engineers and so forth talk about differential equations and write in the language of differential equations many times, because it's easy to describe situations using differential equations, but it's not very useful for actually finding out information about the situation. That's where the solution to the differential equation comes in. Okay? And that's what we're going to use right here. All right, so first we have Boris. Let's look at his situation. And we have Natasha. Let's look at her situation. And what we had was what, 2 different cups that they had their coffee in? And so Boris had a K value of negative 0.05, and Natasha was negative 0.08. Right? So it's really like doing 2 problems in one. Okay? So they had their coffee. What was the first situation? They took it outside in Frostbite Falls, Minnesota, or whatever. Right? And so the room temperature in this problem would be the outdoor temperature, which was negative 10. Right? So we start out by going y equals negative 10 plus AE to the negative 0.05, so it's nice, we already know the K value, so that's a nice start. A lot of times we don't. Okay? And then times T. And Natasha would be y equals negative 10 plus AE to the negative 0.08 times T. Right? So that's kind of our starting point for each one of them. All right? So Newton-Von-Coulomb is all about just knowing the equation and then plugging in numbers at the appropriate times and solving on your calculator. That's all. It's really, once you get to average, it's just quite easy. There's not really many or any tricks that can be thrown at you in these problems. Okay? So what's the next thing I do? What's the next thing I do from here? Find A by doing what? What was the initial condition? Y of 0 equals 90 degrees. The coffee started at 90 degrees. Now, listen, I really think if you're struggling at all or having any issues, I really think it's good habits to get into, to be writing down the equations and stuff like that. It can help avoid confusion. But if you can look at this situation and you can say, hey, I'm going to plug in a 0, this is going to be this will be 90, I'm going to add 10, A is going to be 100, and without writing down, you can tell that A is going to be 100, and go right to that equation, that'll be fine. But here's why A is going to be 100, because we're going to put a 90 in for Y, and we're going to put a 0 in for T, right? And so, yeah, and so right here, E to the Z, oh yeah, plus, plus there. And so E to the 0 is going to be 1. So this is going to be 90 equals negative 10 plus A. So A is going to be 100. So the equation becomes Y equals negative 10 plus AE, nope, not A, 100 E to the negative 0.05 T. And the same thing is going to be true for Natasha. Right? Because when you put a 0 in there, the K doesn't matter. Right? When you put a 0 in for T, the K doesn't matter. So this can be e to the 0, which is 1, so we're going to add 10. So we're going to get negative 10 plus 100 e to the negative 0.08 T. So there's their 2 equations. One for Boris, one for Natasha. So what were the 2 questions? First, they wanted to know what will the temperature be after so many minutes. Did they say that? Or no?
No.
How long does it stay above 70? Right. How long does it stay above 70? So we put a 70 in for Y. And now you need to be able, on your calculators, to do this. This will be for sure on the calculator part of the quiz. So you just put 70 in, and right from there you can just go to solve. Okay, now according to the answer book here, this came out to be, and they didn't do a very good job in the answer book of doing like 3 decimal places, 4 point something. No, that's the wrong one.
No.
So it's 4 point what? Okay, 463, 462. So it takes that many minutes, and for hers, so we would put, again, we'd put a 70 in there, equals negative 10 plus 100 e to the negative 0.08. 2.789. Okay. Do I have those right, the numbers? Why doesn't that seem to make sense? Oh, yeah. Oh, he has the better insulated cup. But it's not environmentally friendly, right? He's got the styrene, right, that's what it is. He's got the styrofoam, so he's got the better cup, the better insulating cup, so his is going to stay hot longer than hers is going to be, but hers is more environmentally friendly. That was the idea. Okay, then it said after so many minutes, 5 minutes. So at that point, you just plug a 5 in for t. I mean, those are really the only two things you can do, right? You can plug a value in for y and solve for t, or you can plug a value in for t and get y. I mean, that's what we do, right? That's what we do. And of course, the reason it's relatively easy, if you look at this, there's really no calculus in that problem at all. There's any. The only calculus is going from the differential equation, which is this, that's the calculus. Going from the differential equation to the solution to the differential equation. That's where you need calculus. Well, this one we just memorized. We didn't even show you yet how to solve it. Now, later in the year, we will. Later in the year, I'm going to show you how to go from this, okay, to get to this. We're just not there yet, okay? So really, once I have this equation, anybody that's worked with ease or whatever, we don't have to do that. All we have to do is then type that into a calculator, right? So just getting comfortable working with this equation and so forth is the thing. And then they say, okay, what if they stayed inside the store? So that's going to change what? Big T. So instead of -10, it's 25, and so that's going to change A then, right? So A will be different, right? And it's just like, so it's almost like getting to work Newton's law of cooling 4 times in this problem, right? So practice. It's just practice, right? But so that's kind of why I signed that one, and the numbers are all here for you to look at and so forth. One of the things, and then the last thing I guess they said is, in part C, they said, if it was going to stay above 70 for 5 minutes, what K value would you need, right? So if we want to look at that, if it's going to stay above 70 for 5 minutes, now this was outdoors, right? So this would have been -10 plus 100 e to the k times 5, right? So we want to know at what time would it be 70 degrees, or what k value would make it be 70 degrees when t is 5, okay? And so you would find the k value, because that's what you normally have to do in these problems, is find the k value. So they usually say, okay, it started at 90 degrees, and then 5 minutes later it was down to 70. So you plug the first one in to get your a value, you plug the second one in to get your k value. And it came out to be like -0.0446 or something like that for the k value. But again, it's just solving. It's just like solving for t. Okay, same thing. All right, and then 24 is another chance to do one of those. They've got like 30 something, 30.5 something minutes, I think, is what 24 comes out to. Here. Okay, so that's just another Newton's law of cooling. So there's nothing trickier than that to be able to do. I guess the only other thing I would say, we did this one back in chapter 2. We did that problem of Torricelli's law. Remember the water draining out of the tank problem? The only thing where we could introduce a little bit of calculus into it is, let's see, in this problem, let's say we had Boris with his -0.05. Y minus, what was the temperature? Let's say they were indoors. No, what was it, 25 indoors? 25 is their temperature indoors. Okay, so let's say we had this. Let's say this was the differential equation for Boris, right, and his coffee, and this is indoors. And what if it said, at what time is the coffee cooling at a rate of -0.3 degrees per minute, or something like that? At what time is the coffee cooling at -0.3 degrees per minute? So what would you do with that information? And they probably wouldn't say negative. They would say cooling at a rate of 0.3 degrees per minute. You'd have to put the negative on it. Okay? What would you do with that information? Plug it in where? That would go in for y prime. Now, would you put it into this equation? Or would you use this equation, which would be, what was this? This was 65 then? Was that the equation when he was indoors. Wasn't that 65 there? A was. Okay. Would you plug the negative 0.3 into the differential equation for y prime, or would you use this? Or would it matter? Well, the differential equation, because you need to plug it in for y prime, right? But I guess what I'm saying is, what would be the problem with that? If I put a negative 0.3 in there and solve, what am I solving for? Y, which is what? The temperature of the coffee. Now the question was, at what time will this happen? So once you've solved for y and got the temperature of the coffee, say it came out to be, I don't know, 72, what would you do with that? You could put it into here for y, right? You can put it into here for y and then solve for t. So that would work. Could I not also do the derivative of this equation? Couldn't I do the derivative of my solution? Let's write that down. So the derivative, or I'm going to write it, you don't have to, but the derivative of my solution would be derivative 25, that would disappear. 65 would just hang out there. E to the negative 0.05t times the derivative of the inside, negative 0.05, right? Wouldn't this be y prime? So couldn't I take my negative 0.3 and put it there and solve this, and I get t directly? Both would be fine. Either one would be fine. This y prime is the same as this y prime. All right? They're both the rate that the coffee is cooling. So that would be the only other thing that'd be a little bit different than what the rest of these problems ask about. Is if I ask in a cooling problem something about the rate that's changing, then you've got to put that into y prime. So you got a choice. You can either use the differential equation to plug into, or you can use the solution. But the solution, remember, is y. So you'd have to do the derivative to get the y prime. But we should be able to handle that. I mean, right? Okay. So that is the stuff for today. In today's homework, that's the stuff we have to be able to do. So let's go ahead and let me pass out. Go ahead and get your calculators out and open up this document that I sent to you called Slope Fields Forever. And I'll pass out this worksheet to you here. Now, to be honest, to do the worksheet, we really don't need the document on the calculator itself. I decided to go ahead and give you the worksheet. I mean, you could have typed everything into the calculator document and sent it to me and so forth. And I thought it'd just be just as easy and probably easier for you if you had this worksheet to write on. So we're going to do that. So you'll notice as you go through this that it will describe things on the calculator document. How much you refer to the document, the calculator document, is up to you. So as we start on this, it says describe your observations when you grab and move the initial condition point on the slope field on page 1.3. So we go ahead and we scoot forward 1.1, 1.2, just kind of telling you what's going on, and 1.3. So we have a slope field, we have an initial condition. So you can go into here. Now on yours, it's a little tougher to do than it is on my computer. But if you grab, the idea is if you grab this initial condition, that you can slide it around and you can kind of see the solution curve change. Okay? So you can see the solution curve. And so that's kind of that thing with the blue dot, we were talking about in our book. You get a different initial condition, you get a different solution curve in that slope field. All right? So you can answer that part of that. All right? Then it says the slope field based on that differential equation, which is this one right here. It says confirm the slope of the short segments on the slope field by finding the value of the slope, and then they give you these 4 different points. Now that's what those 4 answer blanks are for you there on number 2, where you just plug those points in. Now if I go on my calculator document, that would be this next page, Okay, they describe that exact same problem, and then they come over here. Oh no, I guess they don't. Never mind. So it says, oh yeah, I got to scroll down here. I can't. My thing keeps disappearing. So when you go to page 1.4, if you scroll down, so they have places where you could actually type it into your calculator document, but I would suggest not worrying about that. I would just write it on your paper. So every time you have a chance to write an answer to something on here, there's a corresponding page on here where you could do it, right? So that's basically what that's about. All right, and then when you go to the matching activity, now down at the bottom, it talks about a matching activity. Now, if you go to, like they say, if you go to page 4.2 on your document, pages 3.1 to 3.5 talk about how to graph a difference equation. Well, we did that one yesterday. So we don't really have to worry about doing that because we're not going to do that much. That's not going to be on the quiz. You're going to have to graph differential equations on your calculator. All right? So you could, on the back side now of this, you could then on your calculator document go in and type in these differential equations and see what their slope fields look like. Now that kind of defeats the purpose of the matching, but it could be a way to check maybe. Okay? So what we're going to do on the quiz, that'll be a no calculator thing, this matching. I want you to do it like we did today's homework. So you get some practice doing the matching on the back side. Okay? So you don't really have to follow those directions down here. Right, just unless you want to just go into there and type it in and just to check your answers and so forth. Okay, so that part's up to you. All right, so you're going to be working on that, and then the other worksheet that I'm going to pass out to you here, the other practice, is this one right here. And then we'll just talk about it briefly, and then I'll get out of your way and let you work for the last 35 minutes. Get a lot of this done. A few people talked about doing a gateway at lunch. I would let you start that at 11:30 if you want to get a little bit of a head start on that. So. All right, so on this worksheet, it says draw the slope field, okay, which we'll come back to in a second. The second page is a matching, which is kind of different, and I'll explain it here in a second. The last page is a matching like we're used to doing, okay? You've got the differential equations down here. Notice it says dy dx, but that's the same as what? Dy dx same as y prime, right? So the differential equations are given to you as dy dx instead of y prime. But I want to go back to the second page. This is a little different. Match each slope field with the equation that it represents. You go down here, and what do you notice about those equations? They're y equal. So these equations are actually what these graphs are, right? Because remember, the slope field is representing the y graph. And so I'm not sure I would ask you that on a quiz, to be honest with you, but I just wanted you to make sure that you noticed what it is you were finding. All right, so back to the front page. So yeah, I realize some of this gets a little tedious with the number of points, but you need to be able to do this. It's on the AP test. It will be on our test. I will give you a graph like this with some dots. Now, if I remember right, the one I'm going to give you probably has more dots than these do. Right? But at some point, what I'm mostly going to look for when I grade a slope field is there certain key points that I want to make sure have the right slope. But a lot of times you get out to the edges of a slope field, they're just almost, they're a slope of 3, then a slope of 5, and I mean, they're getting really steep. I mean, those I'm not paying a lot of attention to. But the ones where it's negative or it's 0 or, then you want to really make sure you've got those dead. All right, so if we look at this, y prime equals x plus 1 is what we've got. So that means whenever x is 0, the slope is 1. So in each of these dots, when x is 0, we want to do a slope of 1. Right? And then go over to when x is 1. You get a slope of 2. So these should just look a little steeper. And when x is 2, you should get a slope of 3. So those should be steeper still. And again, I'm not going to get real picky on that. And when x is 3, you get a slope of 4, which is really steep. Right? Really good steep. And then you back up, x of -1, that's your slope of 0. So that's the row I'd really be interested in when I grade these. You know, like on a quiz, is I'd really be looking to make sure you have 0 there. And then you go over to -2 plus 1, that's -1. And then x is -3 plus 1, that's -2. So, you know, steeper yet. Right? And then there's your number 1. And of course, the ones that have both x and y in them are the ones that take a little longer because you have to calculate every single point separately instead of just the x's, just the y. Okay, so 3 things for the quiz. Draw the slope field. You got some practice here. Match slope fields. You got multiple practices there. And then, of course, Newton's law of cooling, which is not part of today's homework, but you got to be able to do that. All right, the rest of the time is yours to work and get as much done as you can.
Return to the guidance office.
Oh, yes, yes.